Yes, sir, you're audible.
Oh, sorry. So I didn't realize that my mic was in mute. Okay, I'll go through this question again. Okay, so the question was, in which kind of distribution there is no restriction placed on the number of electrons to be at any specific energy level. So it was like Fermi-Dirac distribution, the classical particle distribution, Bose-Einstein distribution, and Maxwell-Boltzmann distribution. So, uh, so we know that classical particle distribution, so Maxwell-Boltzmann distribution is for classical particles. So both B and D correspond to the same kind of distribution. And this Fermi-Dirac and Bose-Einstein are for quantum particles. For Fermi-Dirac distribution is for particles, quantum particles called fermions. The Bose-Einstein distribution is for quantum particles called bosons. Now, even though these two are quantum particles, there is some difference in their nature. So, for fermions have half integer spin. An example of fermion is electron. We know that electrons have plus or minus half spin quantum number. And a property of fermions is that no two fermions can occupy the same quantum state at the same time. Whereas bosons, they have integral spin, unlike fermions. Examples of bosons are phonons, which are lattice vibrations. We will be learning more about phonons probably towards the end of this course, and also photons, which are light, which is light particles. And unlike in the case of fermions, in the case of bosons, there is no restriction on the number of particles that can occupy the same quantum state. So this is what I had written down till now. So this is the difference between the fermions and the bosons. And because of this difference, there is also a difference in the statistics, the distribution statistics of these particles. So in the case of for the distribution in the case of classical particles by the Maxwell-Boltzmann distribution, the number of particles at energy level EI is proportional to the 1 by of exponential. It exponentially falls down with the energy level. So at higher energies, the number of particles exponentially falls down. In the case of Fermi-Dirac, we write down the probability. So the Fermi-Dirac probability for at energy level EI, Fermi-Dirac, is given by exponentially the energy level EI minus the Fermi energy by kT. And if you want to find out the number of particles, you have to, like, number of particles in the Fermi-Dirac distribution, you have to multiply this probability with the density of states. And in the case of the Bose-Einstein statistics, the option number C, the number of particles is given by proportional to now. If you look at this, in the case of Maxwell-Boltzmann, we have the number of particles. So this corresponds to the number of particles. Whereas in the case of Fermi-Dirac, we get a term for the probability. And if we plot this, we see that the distribution looks something like this. In the right side, so this is the curve for Fermi-Dirac, this one, and the red one is for the Bose-Einstein, and the black one is for the Maxwell-Boltzmann distribution. So we see that in the case of Fermi-Dirac distribution, there's a restriction. There's a restriction placed on the number of electrons to at an energy level. If the probability is 1, you cannot put more electrons. You cannot fill in with more electrons. Whereas in the case of Fermi-Dirac and Maxwell-Boltzmann, you can put in more electrons. And so in the case of Maxwell-Boltzmann and Bose-Einstein condensate, there is no restriction placed, and also Maxwell-Boltzmann is for classical particles. So the answer is B, C, and D in this question. If you have any questions, then you can ask me. Or you can also write it up in the text box. Okay. So we'll move to the next question then. Okay, Bhunesh. So the Fermi-Dirac distribution function is derived including which of these principles? The Pauli's exclusion principle, Aufbau principle, half-spin particles, and azimuthal quantum number. I'll give 30 seconds to 1 minute for you to either think or give me any answer, then we can start discussing. Okay, Pauli is correct. Okay. So when we discuss in the case of fermions here, that no two fermions can occupy the same quantum state at the same time, this is the Pauli's exclusion principle. So you're right, the answer is A. The Aufbau principle is for, it talks about the filling up of this electrons in energy levels. So this is about electron filling. So it says that the electrons fill from to lower to higher energy atomic orbitals, and the distribution does not consider this. So I mean, we do not include this in the dash distribution, so this is not the answer. Half spin particles. Now fermions, Fermi-Dirac distribution. So this is for fermions, and as we had discussed in the previous question, they have half integer spin. So the Fermi-Dirac distribution is also for half spin particles, which are basically fermions. And the azimuthal quantum number. So all types of quantum particles have the azimuthal quantum number. So even like fermions, both fermions and bosons have this. However, the Fermi-Dirac distribution is only for fermions, and therefore azimuthal quantum number is not the correct answer. The answer is A and C. You can ask me if you have any questions, we can discuss. Okay, let's move to the next question then. So we are asking about the definition of anisotropy. The anisotropy in a material is directionality in property. Is this the correct definition of anisotropy? True or false? So the answer is true. So the if there is any directionality in a property in a material, we see that the property is anisotropic in nature. So one of the examples of anisotropy is in the case of electronic conductivity observed in graphite. So graphite is basically stacks of two-dimensional graphitic rings. So they are called graphene rings. So when we stack in top of each other, we get the graphite. And the bonding in the this is the in plane. So this is in plane. So we see that the in plane bonds are covalent in nature, whereas the out of plane bonds are van der Waals in nature. And if you look at the electronic conductivities, the electrical conductivity in plane is very high. So we have very high electronic conductivities in plane. So it's like excellent electronic conductivity. Whereas if you look at out of plane, it's an extremely poor conductor. So we will say that the electronic conductivity is anisotropic in nature in the graphite material. This is for graphite. So this is the correct definition of anisotropy. Okay, so let's move to the next question then. You can ask me if you have any doubts. Okay. So the fourth question is that the Sommerfeld, okay, Bhuvnesh. The Sommerfeld model is better than the Drude model and could be better if it would have included which more of these options: half spin particles, uniform potential experienced by electrons in the solid, anisotropy observed in solids, the isotropy of solids. Okay. The Sommerfeld model or the Drude-Sommerfeld model, it includes the Fermi-Dirac distribution. Which is for fermions. And as we had discussed earlier, fermions have half spin particles. So this option A has already been included. Drude-Sommerfeld model. So uniform potential experience electrons in the solid. So we say that there is no interaction between the electrons and the ions. The electrons are free to move everywhere. This was the assumption in the Drude model as well as in the Sommerfeld model. So even this has been already included. Anisotropy in solids. Now we see that in the Sommerfeld model, we cannot predict the anisotropy. For example, in the case of graphite, there is no way to predict like in which direction we will have higher or lower electronic conductivity. And so the Sommerfeld model cannot explain the anisotropy, and therefore it would have been better if we could have explained the anisotropy observed in solids. And also isotropy is opposite to the option C, so even this has been already included. And because when we studied like CV, conducting specific heat and other properties, we considered the electrons are moving, they're colliding with the wall, and then they're coming back. And all of this analysis did not involve any kind of anisotropy in the system. So the isotropy has already been included. The option is C. Okay. So let's move to the next question. The number of states available for filling the particles are determined by approximating infinite potential energy well of a material. Is this a true statement or a false statement? So the statement is a true statement. So if we draw the potential of electrons in the material, so this is the x-axis, this is the y-axis, this is position, and this is the potential. This is zero potential. And if we draw the potential of an electron, so let's say the particle, the solid block starts from here, and so we can draw the potential like this. And so on and so forth. So this is a solid of length L. This is how we can draw the potential. This is where the ionic cores are located. And if you want to find out the number of states available, what we do is we say that if we again draw one of these wells if we draw, or it will be, we say that the potential inside this well is 0 and the potential outside is infinite. And so this is of like dimension A. So we have dimension A. We can also draw for the entire solid object of length L, and even in that case, we'll say that this is 0, this is L, here it's infinity, here also it's infinity, here it's 0. So we approximate this potential well to have infinite potential energy, and the statement is true. Also, the solution, you know that the solution of this is, if I've gone through the lecture, it's like the state is n. In this case, it is n pi by a. This case, it is n pi by L. Now L is much greater than A, so A is in few angstrom, whereas L can be in millimeter or something. And so if you find out the number of states in here, you will see that the states are very much located far from each other in this uh, potential wells, whereas they are very closely located in here. So we will be discussing more about this potential wells in the upcoming questions. So yes, so we consider infinite potential energy as an approximation to find out the number of states. So each of this is a case state. So the next question is, the potential of an electron determines its state inside a material. Zero potential energy of an electron in a solid of 1.1 centimeter length indicates that which of this following? Electron is bound to move within 0.8 approximately nanometer scale within the solid. Electron is bound to move within approximately 1 centimeter length within the solid. Electrons is free to move anywhere till infinity. Electron has escaped from the solid. Okay, so we will redraw this potential energy once again to have a clearer picture. So then we have the position in the x-axis, potential of electron in the y-axis, and we can draw the electron potential in this way. Okay, so this is the zero potential. Okay, now we saw that. So now we saw that in the previous question that there are some states which are like far spaced here, and in here we have the positively charged atomic cores, and so in these locations you have bounded electrons, and the spacing is given by n pi by a. In the case of in this regime, this is the entire length of the solid. So we have from 0 to L. If L is the length of the solid, so the states are located much close to each other. And these electrons are what? They are the nearly free electrons. So they are contained in the length, within the length L, and the K is given by n pi by L. Since L is much larger than A, so this is A, Since L is much larger than the A, the number of states are located much closer to each other. And then can be some electrons which will have exactly zero potential. So what are these? These are the truly free electrons. So these are the electrons that are at an infinite distance from the solid. So in this question, we say that the potential of an electron determines its state inside the material with zero potential energy. So this is the zero potential energy, which is for truly free electrons. So where do these electrons reside? So electron is bound to move within 0.8 nanometer scale within the solid. So we know that is not the answer because that is for the bounded electrons and they have much lower potential. So this is incorrect. This is for bounded electrons. So the second option is electron is bound to move within 1 centimeter length within the solid, which is basically the length of the solid. And there we see that only the nearly free electrons which have potential energy lower than zero. So even this is the wrong answer because it's for the nearly free electrons. They're still inside the material. And if it has zero potential, then it does not lie in the solid anymore. It is free to move anywhere till infinity. So this is the correct answer, and it has also escaped the solid. So the electron is not in the solid anymore. A truly free electron is not in the solid anymore. We can draw it. It's not in the solid anymore. It has come out of the solid. So the answer is C and D. Okay. Let's move to the next question. A solid having atomic number 79 and length 10 centimeter is kept in a closed room at room temperature. How many electrons of an atom of this material will be able to move within 9 centimeter length and 1 angstrom length? So assume that assuming that each atom gives out one free electron. So one atom. Like how many will be within 9 centimeter and how many will be within 1 angstrom length? So 1 angstrom is roughly the size of an atom. So this, in the previous question, this A is roughly 1 angstrom. And so as we have seen here that this has only the bounded electrons. This contains only the bounded electrons within 1 angstrom, within the dimension A. So if there is only 1 electron per atom, then in 78 of them will be within 1 angstrom length. And since the total number of electrons per atom is constant, So 79 minus 78 equal to 1. This one free electron, one electron per atom will be within nine centimeter. And so if you look at the options, so one will be within 9 centimeter and 78 will be within submitted bounded electrons will be within the size of the atom, the 1 angstrom length. Okay. So we'll move on to the next question. Do you have any doubts till now, Bhuvanesh? Okay, okay. Thank you, Bhuvanesh. So the next question is a true or false question. So the work function of a material is same as the Fermi energy. Is it a true or a false statement? Okay, so we'll redraw. So we have redrawn the previous diagram. This time we have magnified the potentials. So if you draw the states, we see that this time number of electrons, the electronic states. So this is for the bound electrons, and for, as we know by now, that for the case of nearly electrons, the states are very closely located. There's a maximum energy EF till which all the electrons will be located. So at 0 Kelvin, so at 0 Kelvin, EF is the maximum amount of energy that electron can have. So maximum energy are the state that electron can set in, and this is for truly free. Now, and this difference in energy between the Fermi energy and the zero potential is the work function. So the work function is not same as the Fermi energy. So if you have to define the work function, we can write it as So first of all, the work function denoted by phi. This is the work function. And so this is basically the Fermi energy given by EF minus the zero potential. So this is with respect to the escaped electron. So you take, once an electron is sent from the Fermi energy to the infinite distance where it faces zero potential, this difference is the work function. And therefore, the answer is false. Work function of material is not same as the Fermi energy. And so, if we have to write down a definition for the Fermi energy, we can write that it is the least amount of energy required to pull the highest energy electron available in the metal So this is basically the Fermi energy. Fermi energy is the at the Fermi energy, the highest energy electron is located. And take it to infinity. Infinite distance with respect to the solid. So this is how we can write down the definition of not Fermi energy, so the work function. Okay. So next question. The impact of quantum mechanics is observed clearly in classical particles such as marbles, demonstrated only in particles which are only if particles are identical, demonstrated in particles showing both particle and wave-like behavior, demonstrated in subatomic particles showing particle-like behavior but not wave-like behavior. The quantum mechanics is basically for particles showing both particle and wave-like behavior. We had discussed in the previous question also. So option B would have been correct if it would have mentioned that it's for particles which are identical and indistinguishable. If this condition was also is there, then even option B would have been the correct answer. And for classical particles, we have the Maxwell-Boltzmann distribution. We have the Maxwell-Boltzmann distribution, and so quantum mechanics is not for classical particles; it's for quantum particles. And Particles have to show both particle and wave-like behavior. So option D is not correct. It is the opposite of option C. So the answer is option C. Okay. This was an easy question. So the next question. According to the Drude-Sommerfeld model, only dash participates in the process of on increasing the temperature. Electrons close to Fermi energy, electrons just above the Fermi energy, all free electrons, some of the nearly free electrons. So the Drude-Sommerfeld model is same as the Sommerfeld model. So as we have discussed, it includes it considers the Fermi-Dirac distribution. And if we draw this distribution, we see that if this is the Fermi energy, if this is 1, this is 0, so at T greater than 0 Kelvin, we have a distribution. This is like 0.5. It goes up something like so. This is the distribution. It doesn't go below 0. It stays at 0. It cannot go below 0. And so on increasing the temperature, as we have discussed so earlier also, this transition cannot take place because there is no available state at this location. So even if the electrons want to gain energy, they cannot because there is no available state as such. Whereas electrons can go from here to here. So close to the Fermi energy, these electrons can participate, as well as from in this area, above Fermi energy, lower Fermi energy, around the Fermi energy. So in this regime, the electrons can absorb energy, and therefore, so electrons close to the Fermi energy participate. It's true. Electrons just above the Fermi energy. So we know that just above as well as below. If this was the option, then it would have been correct. But it's not written, so option B is wrong. So all free electrons. So the Fermi-Dirac distribution is for the nearly free electrons. This is for the free electrons. But we see that even if it's of free electrons in this distance, they cannot participate in the energy gaining process. And so therefore, all the free electrons cannot participate in the process. And so this is wrong. And only some of the nearly free electrons can participate, which are near the Fermi energy. So the answer is option A and D. Is there any question or anything? Okay, so we'll move to the last question. So we wanted to discuss this question in the last class. One of the students had a question, but unfortunately we had run out of time. So we'll discuss it in this class. So if this is the data, so the n bar is represents a microstate. So there are different microstates: n1 bar, n2 bar, n3 bar, and the probability of occupancy at energy level E for a specific n bar is for n1 bar it's 0.7, it's 0.35 for n2 bar microstate, and for it's the probability is 0.48 for n3 bar microstate for occupying the energy level E. There's also the probability of one of these microstates existing. So if this is the data, then which is the most probable microstate of the system? So we see that the probability of microstate n3 bar is almost close to 1. It is 4 orders of magnitude, or 4 orders of magnitude higher than the option A and options n1 bar and n2 bar. So n3 bar is the most probable microstate of the system. Second question is, which is the microstate with the lowest probability of occupancy? So we see that microstate with the lowest probability of occupancy is n1 bar. And so what is the overall probability of occupancy? So we can write it as 0.7 into 10 to the power minus 4 plus 0.35 into 9 into 10 to the power minus 4 plus 0.48 to 0.99. So we know that the most probable state is the equilibrium state. So these two have like zero significance compared to the value that this will give, and hence only this is important. This becomes the equilibrium state of the material, and the overall probability can thus be given by this multiplication, which gives 0.4795. So yes, so this is the overall probability of occupancy of a state at energy level E. So these are all the questions that I had for today. It's almost 4 p.m. So do you have any questions? Do you have any doubts? Bhuvanesh? Okay. Okay, so we can stop here. So many of the students did not come to this class. They can ask me if they have any doubts in the next class, and we can revisit these questions somewhat more if required. Okay. Thank you, Bhuvanesh, for coming to the class. Let's stop it here.